I'd like to now welcome our second speaker of this morning's session, Ben Leclerc. Ben's joining us from Invox Respiratory Innovation Centre, where he's been since 2023, and he's working there as an engineer in the Respiratory Innovation Centre in Belgium. His research is focusing on the physical aspects of soft mist inhalers. It's a very prescient subject right now, and his aim is to develop a good understanding of the involved microfluidics and droplet formation. This morning, Ben's going to talk to us about controlling droplet size and spray duration in SMEs. Thank you very much. Over to you, Ben.
Thank you. So, stay close enough. Welcome, everybody. So, I'm going to talk about this research that we did on how we can change the nozzle design of a soft mist inhaler to play with the droplet size and the spray duration. So, first of all, I will explain something about the principles of soft mist inhalers. After that, I will explain our experimental setup. We will vary the impingement angle first, then play with channel width, and finally, I will conclude and say how we will go on with this research. So, first of all, the most well-known is the Respimat of all soft mist inhalers. It works with a pump chamber. So when you press the button, the spring creates a pressure, normally 250 bar, pushes the fluid through the nozzle, creating two very small but very fast jets over here. They impinge, and during this collision, the kinetic energy is used to overcome surface tension and create droplets. Referring to Wednesday morning, the opening session about the global warming potential of some inhalers, I want to point out soft mist inhalers work completely mechanical. There's no propellant needed in here. So, as I said, we have high velocity jets. They have a parabolic profile when they exit the nozzle, and in the peak, you have speeds up to 200 meters per second. So that's almost as fast as a commercial airliner. There's a typical duration of the spray of 1.5 seconds, and the kinetic energy is so used to overcome the surface tension. For optimal delivery in the deepest area, alveoli of the lung, we need droplets of about 2 to 5 micrometers. If they're larger, they will be deposited in the upper airways. If they're smaller, they might be exhaled again with minimal deposition. So therefore, our question, what effect does the nozzle design have on the droplet size and the spray duration? We used the Softhaler SMI for this research. It has a nominal volume of 15 microliters. We did every measurement with 10 devices with the same nozzle design, and we collected 6 sprays per device. So in everything I will show is an average of 60 shots. We use a placebo solution with EDTA, BKC, and hydrochloric, and water for injection. And we measured them with a Malvern spray deck. We use horizontal sprays, an airflow of 28.3 liters per minute, and we use the mouthpiece adapter at 16 centimeters from the laser. So it uses laser diffraction to measure the droplet size. If I will say spray durations, that's the point between where the transmission drops below 99% and when it rises again above 99%. So with the varying impingement angle, we kept the diameter of the circle constant and the length of these channels as well at 50 micrometers. And then we saw that the droplet sizes are larger for the larger impingement angle, where I want to also explain that DV50 actually is in the cumulative distribution, the point where you cross the 50% line, and analogously for the DV10 and DV90 are 10% and 9%. So they all give more or less an assumption of an estimate of what the curve would look like. The errors I'm giving are the 99% confidence interval. We also see a slight effect on the spray duration, but it's not really as big as what we will see with the channel width. Now, these results, can we compare them to something? Well, as far as I know, this is the first time that it's really been doing with real soft mist inhalers, but there are some simulations available by G et al. From 2020. So they also played with the impingement angle. And what they saw is that the particle size at 90%, so the standard angle, is larger than either for the 81 or 99%. The remark difference is that they kept the distance between the exits constant at all times, whereas for us, since we kept the channel length and the diameter of the circle constant, for us the distance between the exits is changing. So our impingement points, as the impingement angle changes, the impingement point comes closer to the nozzle. They also played with the exit distance. And there they see that the particle size is smaller for the largest exit distance. So we can conclude that in our case, we see a combined effect of both these studies. Then we played with the channel width. Still, we kept the diameter of the central circle the same. We used the standard impingement angle of 90 degrees. And we had the standard channel of 8 microns wide and a smaller channel of 56 microns. We see that there's a big effect on the spray duration that is longer for the smaller channel. But remarkably, if we look at the particle size, there's not really that big a difference. Although you might think that smaller channels are, the fluid goes slower and you have larger particles. So what can we see again from G et al. With their simulations? We also see that for them, the effect on the particle size from different channel widths is not really that pronounced. To understand this better, why does the channel width not affect the particle size? We applied our CFD model to the nozzle, and we found out that although that the flow rate in microliters per second changes, actually, if we think back of that parabolic profile here at the exits of the channels, the speed in the center is still more or less the same. And this has to do with the fact that for a soft mist inhaler, you're not using the pressure really to overcome the viscosity and push your fluid through the small channel. But as you're pushing through the small channel, you need to accelerate it. And your pressure is just the force to accelerate your fluid to these high speeds. So we see that the exit flow is different, as I said, but the speed at the center of the jet is comparable. So what can we conclude for this? We can more or less change the droplet size by changing the impingement angle. We can change the spray duration by playing with the channel width. So this gives us the ability, if we have a new API and we see that our droplets are too large or too small, we see that the spray duration is getting too long or too short, gives us some ideas how we can just change our nozzle. In the current approach, as I said, we changed the impingement angle together with the exit distance. So what we want to do in the future is also play with the exit distance and the impingement angle and the channel width and combinations of all these to collect many more data and have better conclusions. This is the onset of the research. So for that, I would like to thank my co-authors who actually did all the lab work that I'm presenting here. I would certainly like to thank the board of the Invox Respiratory Innovation Center that they give us, besides development, also the opportunity to do this kind of research. And anybody else in our team for their support. And of course, it's not on the slide, but the DDL conference for giving me the opportunity to present this. So I'd be happy to answer any questions.
Thank you, Ben. Really interesting talk. Does anybody have any questions? So please get to a mic or put your hand up and a mic can come to you, or feel free to use Slido as well. Okay, I guess, well, Dave's got one. Can I see anybody with their hand up? It's a bit difficult to see the lights. Okay, I mean, I've got one. I know you've got one as well, haven't you, Dave? I suppose for me, the bit that I found quite interesting is your placebo formulation that you used. I'm curious to understand how that formulation, sort of how representative it is of a typical formulation you might anticipate having in an SMI, and any, based on what your experience, what you know, what characteristics of the formulation may influence or interact with that novel design and impact your learnings and what you know about other investigations that you've done.
I'm sorry.
So I got a long question. I was curious to understand about the placebo formulation that you used and how representative it is of a typical SMI formulation, and any factors that you're aware of that could influence the findings that you've showed, for example, viscosity or some of the other liquid characteristics.
Well, the placebo solution is based on a certain API of interest that I'm not going to name at the moment. But as we compare to the original API, we find similar results. And yeah, it is for that matter representative. But what we're really interested in is how can we, with the nozzle, play around. So for a different API with a different nozzle, can we get the same droplet size and spray time with a well-tuned nozzle?
Okay, thank you. Dave, have we got any in the audience? Can't see any in the audience. Over to you.
Hello, Mike Holroyd. Is it just a happy coincidence that SMIs happen to produce droplets in the 2 to 5 micron range? Because the levers you were pulling were really making quite small changes around that sort of median size. And if you had a formulation that was suddenly outside that range, have you got a lever that you can pull that will get you back in that range? And if so, what might that lever be? Is it down to pressure? Is it down to making gross changes in nozzle geometry?
So,
Sorry, did you not get that?
Yeah, no, can you repeat, please?
Okay, so the levers you're pulling only make a small change in the particle size around the respiral area of interest.
Yeah.
So is there a lever you can pull that if you're way outside that area will get you back into that area of interest? And what would that lever be? Is it, because obviously the small changes to diameter or whatever are only making marginal changes to particle size?
Well, yeah, you can start to play around with the pressure. That's something we also experimented with. Problem is, if you want higher pressure, you need a stronger spring. So the actuation force increases, which is not always good for the user. And the other part is you have all these plastic components. They have to handle a larger force. So you might have to redesign those. So indeed, the range where we can play with it is limited. But as we are only changing the design of the nozzle, it's just a very small change to the whole device.
Do you plan to look at different viscosities and how far you can go with the changes that you can make to manage those viscosities?
Not at the moment. I mean, these are just preliminary results of research that is ongoing, but I hope to have in the coming time better answers to your question.
Okay, thank you.
Okay, thank you. And I think you actually asked one of the questions which came through on Slido, so there's a lot of commonality, I think, within the audience. Okay, we've got time for one last quick question, please. No?
No. Yes?
The droplets in the modeling size are 20 to 30 microns in comparison to the less than 10 microns that we see. Have you got any idea what might be behind that? And I know actually those data are laser diffraction data correlating with the modeling. And I'm trying to get to the bottom of where that comes from.
Well, I think, yeah, if you start modeling, there are a lot of physical parameters that play a role. For example, with the surface tension, that becomes very important in that case. So, yeah, how reliable is actually the model? That's the question. So that's why I only looked at it qualitatively and not so much quantitatively to see, do we see a comparable trend rather than do we actually see the same numbers, because I need to dive deep into actually the modeling and the reliability to be able to compare those.
But I think that they did laser diffraction, and those data show excellent one-to-one correlation between the modeling and the laser diffraction data. But the laser diffraction data is like twice the size of what we know comes out of soft mist. So there's something kind of weird in their actual measurement as well. That's probably good if people know that.
Yeah. Okay.
I think that's obviously clearly a good point for discussion, but maybe in the interest of time, maybe touch base with Ben during the break. So I'm now going to hand over to Dave. Thank you very much, Ben.
One
Great
thing
talk.
I want to
Thank you.
say, I have also a poster hanging with a summary of this talk I gave, so we can meet there if anybody has any other questions.
Okay,
Thank you.
Thank you very much.